Alright, this is the first example shear mode diagram where we had a non-zero distributed load, and it does make things a little bit more complex to work with. Okay, so we have our peak load intensity out here to the right. When we go do our equilibrium, if this beam span is L, then of course the reaction here will turn out to be 2/3 of the total. So 2/3 of 1/2 would be WL over 3, and the other one would pick up the remainder, or 1/3 of that. Right? That's all because that resultant of this triangular load is, of course, at the 1/3, 2/3 location. Alright, so remember here that the slope or rate of change of the shear is equal to the load intensity, and the rate of change of the moment is equal to the shear. Right? Those are important little pieces to always remember. Alright, so now let's go look at the shear diagram. Right? So it's going to start off at 0. We don't know what the units are because this is a symbolic problem. Right? So start off at 0, it's going to follow the reaction, which is WL over 6 going up. So we end up with a positive shear, WL over 6. Now, the intensity of the distributed load is 0 right there. Right? So that'll be kind of interesting. And then note here that the shear is the integral of W dx. Now, the load is a linear function. So if that's a polynomial of order 1, we integrate it, we're going to get a polynomial of order 2, right, throughout this whole thing. And again, that means that we have a function of x squared here. Right? And so this is not going to be a straight line from beginning to end. We do know that we've got W over 6, and then let's see, the integral of this triangle would just be 1/2 of the base times the height, which is, of course, WL over 2. And so WL over 6 minus WL over 2, because this load's going downwards, is going to put us over here at negative WL over 3. It's just a matter of how do we get there. Well, note we start off at 0 slope, we end up with a big negative slope, and that negative slope for shear, right, dV dx equals W. So you can't look at the shear of the loading function. That's not what matters. What matters is that we've actually plotted here how the slope of the shear diagram changes, and it gets more and more negative. Right? So we start off with a flat region that then curves downwards, gets more and more negative in its slope. We don't know where this location of 0 shear is, and that's going to matter to us. So we do need to find it. Why do you say do we need to really find that? Why does it matter so much? Well, here's why. Because what the load diagram did to us to understand the shear diagram, well, the shear diagram is going to do that again for us for the moment diagram. Right? We're going to start off with 0 moment at the left. We need to end up with 0 moment at the right. And dm dx equals v. So the slope of the moment diagram starts off with a big positive, ends up somewhere with a 0 slope, and then it falls back off to a negative. Huh. Well, how about that? And it's a smooth transition. It climbs and gets less and less slope as we go along till it reaches its maximum, and then it had better than fall off and come to 0 at the far right end, matching the boundary condition that we got over there. That's what it's supposed to do, and we're going to integrate now a second order curve, and we're going to end up with a third order curve. We need to find out what this value of M max is, and we're going to find that. We could do it a couple of different ways, but one of the ways is, let's go find out where that shear is 0. And we can do that by coming along and doing a free body diagram associated with this, right? Which would look something like this. We've got a triangular load on the system. We have zero shear by definition at this location to where we have the max moment, so we need to find out what that x value is. Reaction at the left is WL over 6. The moment, of course, is our max moment, and we need to find out what that peak is. It's not W, right? He chopped this off someplace. We're over here someplace now, right? Well, it is just a triangle, so it is going to be proportionality here, that x compared to L, that fraction of where we are along times W naught will be the height that we have right here. Right, so that's what's going to enable us to figure out what x is, because we can sum forces in the y. Right, we've got WL over 6 minus then the change in the shears given to us by this load, 1/2 of, well, because this is a triangle, right? 1/2 of the base, that's x, times the height, that's W naught x over L. And note that our shear here is 0, so there's nothing to add. So that means that whole thing equals 0, just like that. And what we'll get out of that then is that, of course, the W's cancel out here, and we'll have then that x squared equals L squared over 3, right? The 2 over the 6 becomes a 1/3 in there. And so therefore x is equal to L over the square root of 3. The negative root will have no meaning to us, right? So that'll tell us that. Now, if you remember how parabolas work, this area is going to be 2/3 of the base times the height. So 2/3 of L over square root of 3 times the height is WL over 6. And let's see how that works out. That's a 2 there, that's a 3. That will equal WL squared over 9 root 3. I'm just looking that up in our various property tables for parabolas. And so that would tell me that M max would then equal WL squared over 9 root 3. What if you didn't remember that? Or you didn't have that table available to you? Well, you could just sum moments and find that, right? It doesn't matter if you go to the left or to the right. Let's go at that x location, and you'd have minus WL over 6 times what this x distance is, which is L over root 3, and then plus the 1/2 of the x, which is L over root 3 times W times L over root 3 times 1 over L, that's just the total load, times its moment arm, which would be that 1/3 distance, so that would be L over 3 root 3, right? And then plus M, set that equal to 0 for equilibrium, and you're going to turn out to get the exact same thing as we found through this little shortcut that we took. Right, so that'll get us to the positive maximum moment. Now, how do we know for sure then what happens there? Because we got to find that negative area. Well, that's not so easy to find. You could break that into a triangle and then this little small second order curve. And because you know the intensity right here, you could find it, you could figure out what this height is. That looks kind of complicated. But hey, you know what we could also do? Much more easily, we could follow the same overall approach. That total area, this total bottom area, this plus that, is going to be, again, 2/3 of the base of L times the height, which is WL over 2. And then we'll subtract off this WL squared over 9 root 3. And we'll have WL squared times 1/3 minus 1 over 9 root 3. And then we got to find that common denominator. This is a pain, right? 9 root 3 minus 3 over 27 root 3. and that looks ugly. But what we're going to find, what are we going to find here? What we're trying to find is all of this area that's here, and then we got to subtract off that from this square. Oh my gosh, which is WL squared over 3. Get rid of that. Wow, I mean, it's a lot of work and effort to prove. It's going to show, it's going to come out for us. I know. How do I know? Because look at this. All that mess that was there, but that was 1/3 minus 1 over 9 root 3. But when I take this minus that, that goes away. That becomes the little last piece that's left over. Bam, that's what I wanted to begin with. Right? So there's a way to show it. What I would just do is probably the free body diagram approach. I do this to get to here, and then from there I can check to make sure I have the right maximum moment by doing the equilibrium, and bam, I got it. Okay? Not sure about all the details of that? That's what you need to study. Go back through every last little piece and prove to yourself it really does work that way. Prove it to yourself once, you'll never have to go through that again. If you just take it on faith that I'm right, I bet when I come to a new situation, you'll get fouled up on it.